collapses or the machine gets stuck, and there are many possibilities just because of the uncertainty of the underground. I mean, we are talking about geotechnical engineering here. So who is taking the responsibility, and what does it mean to be responsible for the results?
Thank you for your kind comments. I think, well, in the future, so I had to look in the future for this. It's a very good question. Engineers are still required to sign things off. So if you're more senior and you're chartered, then quickly get chartered, because then AI won't take you over so quickly, because you need someone to put up their hand and say, I'm going to go to court. So AI can't do that yet. AI can't go to court. But in the future, what I see happening is that companies, AI companies, will sell services for data interpretation. And they will be liable, but they'll also offer a service. The other question is, like, who will take responsibility if machines aren't used and something goes wrong? So it's like if machines or AI empowers us, to a greater, basically speeds up the reaction. In fact, like almost takes actions before we could even react and can even preempt things happening, then who's going to take the risk for people not adopting that?
So the question is whether the machine can replace ingenuity of the engineer, can replace invention, can replace ideas. If you take Elon Musk, for instance, and his ideas on how to develop habitation on the moon or on the Mars and so on. So that means that, in my opinion, the machine cannot replace the ingenuity.
AI-powered cars, AI-driven cars. So, I mean, Uber are already partnering with a AI firm who do autopilot cars, and they're self-driving cars, and Uber drivers would be kind of made redundant. So you get an Uber car and you're trusting it with your life. It's driving a car and construction sites have similarities, and I see it happening. Maybe not so soon, because construction seems to be a bit slower than other industries, but nonetheless, the performance is increasing pretty rapidly.
Okay, thank you.
Thank you.
You're going to regret this, Rick. I'm sorry, but you said you had zero tolerance for error. Was that right?
Incorrect data.
Yeah.
Incorrect data.
Yeah. I can't contact you because on the left-hand side of the screen it says richlaver@maxwell.com, and your card says rich.laver@maxwell.com.
I can explain that one. So when I first started the company, they set up my email wrong, but rather than give me a new email, they set up a forwarding one. So both will get there.
They'll both work.
Yes, they will, yeah. Good spot.
We would like to resume another lecture, and this will be presented by Dr. Om, Dr. Tayanan. He is currently a managing director of the EDE Company Limited. Actually, he earned his bachelor degree and master's degree from Chulalongkorn University and PhD from Hong Kong Science and Technology University. He has over 20 plus years of experience in piling, deep excavation, and soil improvement. And he is a subcommittee of Engineering Institute of Thailand. So, Dr. Om, the floor is yours.
Okay. Thank you, Kun Saw, for your kind introduction. Okay, sorry, Kap. So I'll do my presentation in English, even in Thai. So just bear with me for half an hour. So as you listen to very wonderful presentation this morning, it's like monitoring, AI, and anything. So this one will be somehow, I would like to present how could we reduce some excavation-induced movement on the wall and on the adjacent structures. So here are some of my contents. I wouldn't read them all as I think I have a lot of slides and I have to fit them within 25 or 30 minutes to keep you away from very bad traffic. So here's a typical construction in Bangkok, whether we can do bottom up on your left or top down on your right. And as we can see, Bangkok and many cities are very beautiful on the surface. So it's a philosophy that we try to make everything become very messy underground. So soil structure interactions always happen when the superstructure or any other underground structure was built first. When you have any changes in stress, it causes a ground movement, it would cause the other structure to be affected by stress change. So I have listed some possible problems on deep excavation. Actually, they are from large to small. It could be worse, like we have seen in recent years for structural collapse, but I won't be talking it today. It's still too hot to talk. We will just wait it to cool down a little, like what we have seen, like Singapore Nickel Highway. It took 10 years for them to release a report. So the recent case in Thailand, we may just need to wait for some years. And there are some soil movement close to the retaining wall that would affect the buildings. Some misalignment of retaining wall, but I would not talk about it. Hydraulic uplift. Professor Nopadon already gave some a lot of information about that, and Kunarong already present about concrete in diaphragm wall and ball pile. So I will just touch a little bit for the vibration. It wouldn't cause a structure failure or any cracks, but this kind of a small thing that could make people stop you from working. They would just make noise in the social media, go to the district office and stop your work easily. So even a small thing I would like to emphasize today. So we will go for the very obvious and very dangerous one, structural collapse. It's not like every year's incident, but it still happens from time to time. Like to start very early days. That was in 1997. Maybe there are young engineers here. Some of you were just born. It was one of CIFCO's project. Kunarong may be able, a better person to deliver this information. So CIFCO was the one who was awarded to do the diaphragm wall to make a shaft for a pumping station. So the shaft was constructed using almost circular here, but with a polygonal configuration to construct them. So that means it's not a closed loop excavation, not like a normal shaft like Professor Nopadon presented, that they do the caisson thinking that there's a hoop stress to transfer. So in this irregular shape of excavation, there will be a compression force acting on this edge, on the circular one. So they use a temporary strut to use as the bracing system. This is what happened. One morning of 17th of August of 1997, I learned from Kunarong that nobody died, right? Am I correct? No, nobody died because it's they all people here, they just left their house to go to work and then it just happened very fast. So 25 houses were buried underneath this pumping station. That was almost completed. So that time, there was a previous engineer who worked before me as Kun Bin and Professor Pornpot who went to the site. And after that incident, there was investigation. Many people tried to blame CIFCO that diaphragm wall was not good enough. So we tracing back what really happened. So several months before the collapse, the excavation was designed to be excavated uniformly on both A and B side. But as a typical excavator or contractor, they would do the easiest one or the one that they could excavate faster to gain the production in order to claim the money. So they are measured by volume of excavation. So instead of excavate the A and B, the two sides uniformly or parallelly, they focus mainly on the bigger pit. So this caused the stress, the hoop stress, that over the design of the original design of the designer. So when the B part is still full of soil and the A part excavated higher, the strut force that it's acting on the strut was already much larger than the design. And worse than that, we can see the quality workmanship of the connection. We can see there's some gap in complete connection. One thing it was because of the workmanship, and the other thing because it was overstressed. Once it was overstressed, the steel start to deform and the gap provide, and that makes things worse when some part of the wall doesn't attach to the wall. So that means there was some point that there was overstress hugely. And you can see the concrete infill here. If you compare with like Ultimtech, they will not do something like rubbish as this. So this one is much nicer. Much worse than what we are doing now today. And the worst thing was there's supposed to be 10 layers of struts. But this was the day that our engineer, our former engineer before I joined, they went to the site and took this photo and found that the excavation already reached the final depth. We can see this is a sand and there's a couplers connection for the wall and slab connection. It was exposed already. And we found that 3 layers of struts were missing. So that means all the struts with the wrong sequence of excavation and missing all 3 struts. So it's all overstressed and it just happened. So they might call bad luck. I think people might think that they were designing with like 1.6 or factor of safety of 2. But probably they all use up and then that collapse happens. And what we learned is any modification, just ask the designer before proceed to anything and ensure the proper installation of the struts well and really use the robust monitoring system and really use the data, interpret them, and really see that it's warning. Not just, I don't want to mention many projects in Thailand, there was a TOR to read the monitoring system, read the data, and they just leave it in their drawer just forever. So if the engineers there really try to foresee the problem, this wouldn't happen. And I moved from a very long-term projects to a recent one. This happened in China in 2019. So not just COVID happened in China, this happened too. It was an excavation, deep excavation in Nanning in China. So the construction was excavated using a soil nail, 4 sites. The 3 sites looks okay, no sign of excessive movement, but this kind of problem happens, and they discover the sign of the failure just one day. A wide crack of 0.4 meter was observed only one day before the collapse, so that was too late. So one day, so that means they have to evacuate people and just hope that it doesn't extend too far. So this what happened. So that municipal, they assigned, I think, very advanced team of Chinese academics, like Professor Shin was the leading investigator. So they came up with a report, I think within 1 year of the excavation. So they found out that, the excavation was done in sand, mudstone, siltstone. So looking at the geology, it's supposed to be strong enough to withstand the force using the soil nail. But what happened was there was a water pipe that caused a very huge leakage. And that leakage increased the water pressure, and also these mudstone and sandstone, when they are encountered to water, it caused a weakening. Some of cementation was destroyed by water because some cohesion was apparent cohesion. They are good in the dry or with the suction. So once it's saturated with water, so the strength was not enough, and these were expected failure plane. So what they have learned was there was inadequate information on existing pipe. Probably the pipe, they don't know exactly, but from some movement, that movement might cause the cracks on the pipe, and that leakage from the pipe, increase the water pressure and also reduce the soil strength. And the instrumentation, if they provide it well enough, like if they can see the water pressure build up like rapidly, they should be able to interpret and foresee something. But once they discover, it was too late, only one day. So this problem doesn't happen much, but as Ajahn Nopadon and Rich already mentioned, last year we had an incident and many incidents about collapse. So I will move to something that is like happen like almost every day. It's excavation-induced ground movement on nearby buildings. So as we know, so this is one of our projects. Actually, we found that install some inclinometer and observe there was some cracks on the wall and also on the floor. That is normal physics. When you release the load, you did the unloading, so the pressure is on one side, it's on unbalanced side, and when you replace with something weaker, that is a strut or wall that is not strong enough, that the movement occurs and that causes further problems on buildings. So these are soil structural interactions that should be considered, but I won't go through them all. So mostly it's soil and structure stiffness and how they interact with each other and whether we select the method of construction. And somehow we can even strengthening the existing structures to prevent collapse or cracks or even do the ground improvement. So I'll go through some of these by showing some example. So as Kun Saw presented this morning, this is influence zone of excavation, which extend about 2.5 times of the excavation depth. And this is also according to Department of the DPT, it's called Department of Town Planning and Public Works, that they specify that any excavation, any buildings within 3 times of the excavation depth has to be monitored and calculate for the effect of excavation on the nearby buildings. So for numerical analysis, normally people will check the strength, force in walls, movement, settlement, and stability for factor of safety. And in order to see what happened on the nearby buildings, so we have to model on the structures, either try to mimic what is but we cannot mimic the whole buildings, might be too complex. We might try to model the major structure like beam, columns, and piles, whether it can be done in 2D or 3D. That's now computation is now very powerful. Only we engineers should not just be too happy. Once we receive the data from our analysis or even AI, like what Rich just showed us, we have to get some verification from those numbers. And in Thailand, we specify that the distortion angle of the buildings could not exceed 1 to 500. So once we calculate, we'll set up the trigger levels and also the plan observational method, whether we are going on the danger zone. That means we have to put more countermeasure. For example, reduce the spacing of the struts and do zoning excavation. Or we are going on the too conservative, I mean going on the green line, that we know that we are too far from our prediction. That means we can relieve some constraint. For example, going faster, or even like you can remove some struts if the data really show this way, that you are too far from the design line. So the instrument is very useful for a geotechnical engineer. So those instruments is just not too many projects in Thailand that I don't want to mention, that they just read and put those in the drawer. Actually, it helps us to verify the field performance and ensure safety. And when you have to go to the court, it really minimizes the dispute among the stakeholders, whether those houses will blame or it come from you or come from whatever time. So those instrumentation can be very strong evidence. I mean, if we are doing something wrong, so of course they have a right to sue us. And I will show some of data analyzed in a study, like between 2010 to 2022, that we collect the data from more than 50 projects from mostly diaphragm wall, because CIFCO is mainly working on a diaphragm wall, so we have a lot of diaphragm wall data. But we are also extending some projects, like Kun Rong said, we had some Tom Yam Kung crisis. So there are not many projects, so we have to go for other shallower excavation. So we presenting here sheet pile excavation, pile wall excavation, diaphragm wall, and some diaphragm wall is very thick, like John said. We had some data from 1.5 meter thick diaphragm wall. That was for subway station. And we construct from, we have data from bottom up and top down, but I wouldn't go into all details as time is limited. So as we might be already able to predict that, okay, more rigid wall will end up with smaller movement. That is a normal trend. But I would like to show this graph for our young engineer, that you can use this one for verification of your numerical analysis, whether they are in line. So from the analysis, the thinner wall, thinner diaphragm wall for rigid wall, anything thinner than 0.8, for example, 0.6 meter thick, the movement would be quite large, and as well as pile walls. That movement could be more than 0.5% of the excavation depth. That is, from literature, it's considered rather large. But if we take an average of movement, it will be in the line of about 0.2 or 0.3% of the excavation depth. So if your calculation gets something like very odd, too far smaller or too far larger, you may need to ask yourself that, or anything special for the project, that the data was not in line with the real measure data in Bangkok. And I have to emphasize, this is only the data that in Bangkok. So for some similar condition, maybe like Cha Cheong Sao, Samut Prakan, or even in Shanghai, similar geology, maybe, this graph can be used. And for the wall thickness, once you increase the EI, or flexural rigidity, once the wall is thicker than 1 meter, so once you increase, it doesn't have much effect. And also, there's another effect, time. As we excavate in clay, either it's a soft clay or stiff clay, once you let the wall stay without bracing, there was one project that the excavation was very long. We had a project that was like 4 or 5, the size of 5 or 6 football field, I mean, on the plan. So the excavation time was very long, and the span of the bracing was very long. So after you leave the wall for too long, the movement just increased with time as well. And these are the effects from flexible wall. So I consider sheet pile as a flexible wall. So we can see a very wide range of movement, from very small, like 0.2% of excavation depth, like rigid wall, up to more than 2%, which could cause a problem. So very wide range, and with an average of 1.1% of excavation depth. So the key factor for the flexible wall is, unlike the rigid wall, there are many factors. For example, how well is your connection, what is the time of excavation, 3D effect, corner effect, or even the soil stiffness. That's vary a lot. Maybe this graph, once you get it's too scattered, probably it's very difficult to judge whether your calculation is correct or not from the flexible wall. And there's one number that people like to use is like system stiffness. I think widely used in UK, if I understand correctly. It's a good number that tells for the top top one is wall flexural stiffness, EI of the wall. So thicker wall, you have larger flexural stiffness divided by spacing of your bracing. So from its physical meaning, it's quite straightforward. If you have a smaller spacing of the bracing, if you have thicker wall, you have larger system stiffness. So what this graph shows you for, I will start with a rigid wall. Once you have increased the system stiffness, in the low side of system stiffness, once you increase them, the movement rapidly decrease. But once you reach one threshold, from my data, it shows at about 200. You are not improving anything. You are burying your money into the ground without getting any improvement. So for rigid wall, a number of 200 would be sufficient. So anything beyond that is a waste of money and time for construction. But on the other hand, for flexible wall, even we try to increase the system stiffness up to 1,000, we can see the movement. Or this line is a factor of safety against the base heave still increase, and you can see the variation of data. So the system stiffness itself, it's originated in UK, and they are mainly using a rigid wall, and it's come from the stiff soil, not like soft clay like in Thailand. So be very careful from this graph, that not just to use like system stiffness for the flexible wall. That is vary by many factors, as I mentioned in the earlier slides. And there are some measures to reduce the movement, like Professor Noppadon already mentioned. We can improve the ground. Because once you add the cement on the ground, the stiffness increase. Normally, rule of thumb, the strength will increase by like 7 to 10 times of the original under shear strength. And so as the stiffness, normally they will go like linearly. And this is one project that we did. We did the excavation very close to very rigid MRTA safety zone. So they just put one clause, simple. You can do anything. Don't make the tunnel move more than 6 millimeters. Very simple clause that, but many projects, they have to reduce the excavation depth. They must use very thick wall, or some projects that we did, we increased the number of bracing by 2 times. But this is one of the methods that we did. We improved the soil cement column block on the site that is next to the tunnels that is showing on this orange line. So by comparison, on the left is a movement with the soil cement column, and on the right, it's without soil cement column. So from this, we can see that adding the soil cement column can reduce the movement, wall movement, is the opposite side by 30 to 50%, given that you did that before the excavation starts. I'd like to show one example. This one is a bad example, actually. They did the excavation up to some certain level, and they found that there was water leakage through the gap of diaphragm walls. Diaphragm wall was not watertight enough. Water flow, you mean visibly, you can see it flows through into the site. So what they did was they just did jet grouting on this yellow and orange one, high pressure jet grouting. And once they did the jet grouting, it caused things to be getting worse. They opened up the gap and caused a larger wall movement. So from this one, the late stage soil improvement by high pressure jet grouting increased the movement even like 90% compared to the other side without the jet grouting. So just be careful. I mean, if you read papers and you see the soil improvement works, but just see the context when it already really works. And I will move to the smallest damage part, but it could cause a big damage if the people raise their voice. It's a vibration. So in Thailand, there's an announcement of the pollution control department that there's 3 types of building. There are some certain types of building that you have to go through what we call the environmental impact assessment, or EIA, and you have to control your vibration limits within each type of building. Type 1 is a commercial one, so they don't mind. even the large vibration of like 20 millimeter per second is still within the limit. But more sensitive buildings are type 2 and 3, which are residential, school, hospital for type 2, and historical structure or preserved building that they limit the movement only 3 millimeter per second. And what is a 5 millimeter per second? If you see your glass full of water shaking, that's already exceed very low. So the glass of water on the left, I just took it in my office. So we are piling office. So we're testing our machines every day. So I'm used to it. So I don't mind 20 millimeter. So what? Yeah, not a big deal. But for some people, they complain. And once they complain, and if they really measure the data, it exceeds 5 millimeter per second of the velocity. So once that, they can stop our work. So we have to find a way. So Kunarong tried to have a new idea to construct, because we are working on all the sensitive houses all along. If we don't try to do anything, first option is to go buy many equipments from abroad that it's maybe cost like 5 million per set. And imagine we have like 50 sets of machines. We have to buy these sets. That would be cost a lot of money. So Kunrong and CIFCO and the R&D team came up with an innovative method, try to find a way, and probably it won't go to detail, but we invent the method by not using the vibration or vibro hammer. We do the pre-during and add the counterweight to nicely push the casing down. And once we invent that, we already got the Thai petty patent now in use. So we are using this for what we call low vibration piling in the Bangkok. And this is a figure like to show the red one was our conventional data that we use a vibro hammer. So it's like normal hyperbolic curve. Further from the vibro hammer, the vibration gets smaller. But very common case that the piling could be very close to the neighbor, as close as 2 or 3 meters. Some case we had that problem. So if we still maintain using our old method, so we will be stopped from working because the vibration exceeds the limits. Once we use our new method, so there's no problem after we got these patents. And others, I will go very quick. Also, even making diaphragm wall, there's a part that could cause a vibration when we want to take out what is called the formwork between panels. First, in the past, it might take us almost a day or sometimes 2 or 3 days to really take out this, what we call the formwork or stop end. We have to take out and use a lot of force, and that caused vibration. I think there was one site that we worked near it's a kind of clinic. It's a aesthetic clinic like for facelift or something. So they are very sensitive. I even make a joke, maybe we should let our engineer to just do some facelift for them so they will not sue us. But probably because we are so familiar with the working condition of the vibration, but once we start to measure, we found out that without the new technique, this kind of diaphragm wall with the old method caused a lot of vibration. So we try to invent a method that could cause forming a void to take out the stop end easily. And we also got the Thai new patent that is we use this one to reduce the vibration for diaphragm walls. So just install the void forming and remove that is make things to ease the removal of the stop ends. And these are some of our site data of the site that's a low vibration from using these 2 petty patents. This one show the data in the middle of the site. Some vibration could exceed 3 millimeter per second because we have the trucks, backhoe, excavator, or the running very close to the sensor. But outside of the site, and this one is a historical building that has a very stringent limits and all past the limits that they specify in EIA. So I will summarize my presentation. So the monitoring system, a robust one, is very crucial. Also with the timely manner interpretation that you can foresee and prevent the incident to happen. And the database of any kind of excavation could be very useful for your future work or for academic if we sharing among our society that could prevent a disaster for young engineers to learn of. And selection of the wall type, construction method, and system stiffness, I think we should do the optimization, not go for like really conservative, like John say, like people nowadays like go for conservative to just hide away from those uncertainties. And vibration impacts can be minimized using a good technique. Okay, that's all of my presentation. Thank you very much.
Okay, so thank you very much, Om. Very interesting and very good presentation. So is there any question from the floor? No more? Oh, so John.
Okay. Okay.
Yeah.
Oh, you have, okay, John, please.
Or you want to go back?
Just to defend Singapore, I think when Nickel Highway went down, the report was issued within 2 years. It wasn't quite as long as
Oh,
you.
okay, sorry for that. Yeah, thank you. But what I read is like 2015. Yeah.
No,
Yeah,
well,
yeah.
the report came out within 2 years. And the other thing, just to confirm, the pumping station which collapsed, we were the designers, and yes, they did leave out 3 levels of struts. So, and that was why it failed.
Okay, thank you. Dr. Wagner, you have a question?
I should, you mean?
Please.
Well, but the presentation was so perfect, you know, that I'm totally convinced that every problem can be solved through CIFCO and Dr. Tayanan. So I'm really appreciating and admiring what you have presented and your background. Thank you.
Thank you very much.
Thank you for your kind words.
Okay. Okay, so if we don't have any further, so we have to keep the table. So I will give a token of appreciation to Dr. O. So we have only last speaker who could not come here. He is in England. So he will be presenting online, right, from the room. So whether he's already there or not, Rich, can you contact any? So actually, before he comes in. Actually, Dr. Angus Maxwell is a owner of this company, Maxwell, which two of his colleagues were already present. He's online, okay?
He's online.
Okay, so Angus, can he hear me or? Okay. Oh, can he hear me or can he see us? Okay. So, during waiting, I explained a little bit about it. Actually, Dr. Angus Maxwell, he is a very good, actually he is a geologist, but he is very good with all this data processing things and knowing all this ground movement, tunneling, and things. So he was based in Hong Kong for many years, and then he opened up branches in Singapore and somewhere else. And I think now he's back. Oh, okay, Angus. Good afternoon. Good morning, Angus.
This is my second attempt to get to Thailand. The first attempt was when the Heathrow fire happened last year, and my flight was also cancelled. So it's a great shame that I can't be there with you. But I did want to talk to you about the history, really, that we've had, a lot of it in Asia over the last 30 years, of the role of data within the process of risk mitigation for underground work. So I'm going to share my screen. Hopefully you can see it. Share screen. Okay. So I'm going to talk about the evolution of risk mitigation innovations in Asia and throughout the world, actually, and in particular the role of data in doing this. And the main areas I'm going to cover is what data are we talking about? I'm going to go through then the last is first up. Then secondly, I'm going to be talking about the last 30 years and initially how we got started in this business on some adversarial contracts early in the 1990s and 2000s. Then I'm going to talk about what changed and the role of insurance in that. I'll go through a period during the 2000s when we talked about new delivery methods. Then I'll go through a period where some parties in Asia made some changes and did some different things. I'll talk about the value of independence and transparency, talk about openness in contracts, particularly with regards to data, and then talk about how that openness has led to collaboration and teamwork, and then ultimately about how to manage uncertainty on projects. I'm getting notes on Teams to tell me everything's good. Okay. So, what data and why do we need it? Well, what data is all data? We need all data from construction. And particularly, we can put this into some buckets. We're talking about the context of construction, geospatial setting, factual geology, groundwater behavior. We're looking about surrounding infrastructure. In particular, as said, it's about utility, knowing where they are, knowing what condition they're in, sensitivity of them, background behaviors, is my ground already moving or my building's already moving, environmental factors, and then to be able to quantify the risk in construction, okay? And then target investigation measures to make sure we can quantify that risk. We need prediction. We need to know what normal looks like, both normal in terms of how everything is normally moving, but also normal in terms of what we expect a design to do when we actually build it. And then we need to be able to predict things like progress, predict production, predict quantity, so we can see when things deviating from our expectations. And then when we get into production, we need to have all those records, the records as built, and we don't need them done 2 months after the event. We need them done actually at the time of the works, so that we can draw conclusions as to what my expectation was this, the reality was that. Look at why is there a difference. And then we need to use this data to feed back constantly on the excavation process, particularly in things like TBM tunneling, which can be very rapid, and also with SCL or SCN tunneling, where things happen very quickly. We need that rapid feedback on the work, not just in terms of design, but in terms of production, in terms of quality. Are we achieving what we said we'd achieve? And then ultimately, we need assurance. We made promises to people that we can build this without causing damage. We need to be checking the whole time and keeping all those surrounding people confident that we can do what we said we'd do. So that's the assurance. And there's lots and lots of data. And too often, this data is held in separate little systems all over the place. And the engineers don't have the time to be able to constantly get the data in these different separate silos and put it together into one place. So where did this all start? Oh, and by the way, on this data, this is all data that is your data. It's the data that you observe, you keep as you go from project to project. So it's very essential that you make sure you keep it safely, that you can use it in the future. So, starting in the 1990s, adversarial contracts. Typically, these are sort of ICE type contract where we've got the owner, the engineer in the middle, and the contractor. This particular project was my first in Asia, the Hong Kong Area Treatment Scheme Phase 1, otherwise known as SSDS. It was a fast-track, pre-handover project. Contractors, all risk, pretty much major things were lump sum. Unfortunately, it went to an impossibility arbitration. It was a deep tunnel network, inverted siphon, as you can see here, into the rock. And unfortunately, they had a lot of water. And what happens when they hit water, they really weren't set up to deal with it, claimed the possibility, the contracts were ultimately re-entered, not good for anybody. And problems that ensued from that was that we have to find replacement contractors. By that time, the lawyers were all over the project. Because of the scrutiny, there was difficult commercial closure going forwards, and very high sensitivity from everybody on the project. Now, at that stage, I recognized that data was going to be key. We've got an arbitration to solve. We've got another contract to continue, and we've got to do that with lawyers looking all over it. So we put in place a thing called a tunnel data management system. This was 30 years ago now, and this was aimed to be a common data environment implemented by the supervising engineer. All records, everything, all photographs, all time, everything was in there. Single source of truth, fully audited. So if timesheet said probing was done, there was a probing record. Always up to date, always accessible to everybody, and in forms that everybody could use, which was great. And the great thing about that was that the outcome was that, hey, we can start doing some really useful analysis during construction of where things are going. We can start making predictions. We can start looking at opportunities to do different things. The settlement of claims, even though the lawyers were looking all over it, because the data had been agreed at the time, all we were doing was arguing the interpretation. So that actually made the process of claim settlement much, much easier. Ultimately, the client, the owner, our client, won their arbitration 3-0. There were 3 tranches, they won all of them. The data was then used by the phase 2 engineers, in this case it's AECOM, to plan the phase 2 because of all that granular data. Why use a vertical borehole for a horizontal tunnel when you've got a horizontal tunnel you can use? So you've got all this data, every single meter of tunnel has information. And as a result of that, using that data, the provisional quantities on that second phase came in close to estimate, which was good. For a big drilling and grouting job, that's pretty good. So it gives you a lot of certainty in having that database to use. So back to the early 2000s, problems with insurers. I'm sure everybody realizes or remembers this. Premiums are increasing. This is actually Kaohsiung. This is actually Heathrow Express around about the same time. There was also a downturn in the construction industry globally. It became difficult for insurers to insure jobs, so premiums were increasing. Some reinsurers were threatened to leave the sector due to unacceptable risks. This really was existential for tunneling. And what they did was the British Tunnel Society and the Institution of International Tunnel Insurance Group got together and said, listen, what we need to formalize the way risk is managed on construction projects. So they came out with a code of practice. And this code of practice set out the processes for identifying risks, quantifying them, and designing out or mitigating risk on jobs. It implemented a risk manager, permanent risk manager role on projects, constantly updated risk register, set verification processes, and made sure that risk was data-driven. So in the recent versions, they've been quite clear in their section 6 that computer systems need to be there, which recognize uncertainty, try to quantify uncertainty, and try and remove this human error from the system by using the data. And this increases transparency, and also it invites independent review into the whole process of managing risk. And in 2004, that's when we established the company. We started in Asia, in Hong Kong, Singapore, Australia. This actually is the blue line. This is your Bangkok blue line, one of the earlier jobs we did around about 2011, 2012. You see that no shortage of instrumentation on here, quite a lot going on. In those days, of course, Insight changed to called Mission OS. And this was aimed to integrate all data for underground construction. But in those days, often the systems were separated. So in fact, on this one, we monitored just the monitoring and the progress of the tunnels. That was it, nothing more. So going over to 2006, what happened in 2006 was that the TDMS, the system that I created back in the late 1990s, was written into the specifications in Hong Kong. So as part of the quality management records, they required tunnel data management, which asked for all those things that we had previously done. which was great. So we did a lot of these. The only issue was that because this was written into the contractor specification, you imagine an owner's system put into the contractor's requirements. Contractors thinking, I'm not sure I like the idea of having all this data available for the owner. So it took a while for people to get used to that. But we did do a lot of systems in Hong Kong. And now what we're finding is as people get used to this, they're much more open. They recognize the system, the records need to be there, and they do provide them in good time to the owners. And this is a huge resource, obviously, for the owners, the government, and the MTR in Hong Kong, of data that they can use to plan future projects. So after that, after about 2006, we started seeing a number of new delivery methods. And by that, I'm talking about alliancing. The MTR and Australian roads use alliancing quite a lot. And within these, you have a target cost. A target cost means that you set an initial budget, and then you agree a cost, a target cost, with the contractor by getting them in early. They started looking at public-private partnerships, and the airport link in Brisbane was a case in point that we worked on. The problem with these, I'll say the positive. The positives of these was that cash flow was agreed to meet project challenges. So there was nobody was looking to anybody to blame. There was a problem job, you just fixed it. So it was great for engineering. Problems were engineered out, and certainly was recognised and managed. Observational engineering was welcomed on projects. Great. As a result of that, good systems were an investment for the project. So everybody said, no, let's get good systems in place. This is good for the project. We can do observational engineering, we can do feedback, we can do the things better. The reason these didn't go forward was that when pain happened, these were all pain share, gain share forms of contract. When pain happened, it was too much for contractors. And I can tell you, Airport Link was a 20% loss. And that was too much for both Tees and John Holland on that contract to bear. So they kind of fell out of favour after a while. So as a result, what happened was that most contracts went back to design and construct. And lately, they've got this new thing called progressive design and construct, or early contractor involvement, but still, ultimately, they're design and construct contracts. So the idea was that push all risk to contractor. Now, the problem with pushing the risk to the contractor is you're not really pushing the risk to the contractor. You still have the delivery risk as an owner of the job. What you're pushing control to the contractor. So the contractor now has pretty much all the control over the project and also all the control over the data. It does lead to the contractors coming with alternative designs, and often, because the initial designs are quite basic, and often they are quite basic, the contractor goes out and says, I can come up with alternative, and they will push alternative, which further puts the control over to the contractor. As a result of this, we end up with a large amount of claims, lots and lots of claims on projects. Now, on these projects, the systems were written in by the designer, by the owner's engineer, into the contract and provided by the main contractor, which is okay. But again, if it's written in, it's a client system in the contractor's contract. Sort of, you fight a little bit of a battle to sort of make that sort of as open as it needs to be. And as a result of, I think somebody mentioned the Nickel Highway and other things, what happened was that certain parties came up with new ways of dealing with the risk in these contracts. And I call them control or trust but verify. So we look at the LTA after Nickel Highway. Essentially, they then went to monitoring completely or mostly taken away from the contractor. So an independent party does all the monitoring. Okay. Inside the tunnel, because it gets in the way, still the contractor does some of the internal monitoring, but most of the monitoring externally is done by the owner. The system was developed and run by the owner. Okay, so all the data is completely controlled by the owner, and this is a TEM system. And that was in response to pretty much the Nickel Highway incident, and that then takes it all the way from the contractor. Now, I won't really talk about the pluses and minuses of that, except to say that the contractor obviously must get hold of that data, because ultimately they are responsible to design and construct. They're responsible for doing the jobs. They must have that data. If we go to the MTRC, this is interesting because they have left the main monitoring with the contractor. Okay, so he's free to engage any company to do the monitoring. But they appointed an independent monitoring consultant to do about 15% of that monitoring. So they do a check checking the actual monitoring, we're taking independent readings to check that things are being done correctly. And the system is provided by this independent monitoring consultant. So the first jobs we did, we were actually even independent of the MTRC. We were actually employed by the Railway Development Office. Okay, so we were actually independent of all parties in this. And the reason for that was that by that time, the KCR and the MTR had merged, and there was only one railway delivery company in Hong Kong. And it wasn't a government company anymore. I have shares. So we had an important role to provide that assurance of that. And another thing, and something that Rich is actively engaged in now, is that the independent consultant reviews a lot of the data, provides that independent oversight. Okay, removes those cost, political, and time pressures from people, and honestly, openly looks at the data to identify any anomalies. So, the value of independence and transparency. Turns out insurers love this. Okay, so actually in the negotiations for premiums on certainly MTR jobs, they recognise that this independence and transparency lowers the risk on the project, and it increases assurance for stakeholders having it there, knowing that somebody else, without no hand in the contract, whatever, they're there to look at this. And there are evidence to show that it can reduce premiums on projects. Okay. So let's look at the 2010s. This was a sort of a process of gradual openness and learning to share data. So we started off in Kuala Lumpur on both KVMRT1 and KVMRT2. In the systems we provided for them, it was the instrumentation, the IDMS, the instrumentation data, ground data, and machine data. Okay, so the first time really it was machine and things. So you got that process control coming in. The systems here were implemented to be independent of the data producers. So the instrumentation companies weren't managing the system. That did two things. One is it gave a level of oversight, which was good. Secondly, it put the systems closer to the people who needed it. If the systems are down in the low, the bottom of the subcontractor, there's no way the system provider, who's an engineer, can talk to the user who is an owner or the engineer or the designer. No contractual relationship there. This put it much further up the tree, meant that we could work with Coe.or.th in this case to develop systems to minimize risk on projects, which was very, very useful. And this active risk management, this is just an example of one case. You can see the TBM data here. This is earth pressures in here. And you can see the area here. This is actually where they hit a cast. Okay, so you can see that the casting zone is in here, just happens to be where a viaduct was going past here. So we were looking at this the whole time. Active risk management, feedback on the monitoring, feedback on the TBM parameters, making sure it's okay. And we created live dashboards. He's going across another railway here, and you can see that we're tracking the TBM parameters. You can see that the TBM actually came out of rock a little bit earlier, so just about here, not here. And you can see that they increased the face pressures as they went past this railway above the original design line as part of a process control feedback system. So very useful to be able to have this back analysis of Gaussian settlement troughs, twin tunnels here, everything, high level of control as they went across these important assets. To go to Singapore Power, about the same time we started with Singapore Power, 50 kilometers of tunnel, I think 17 shafts. This was phase 2 of a phase 1. Phase 1 had given them some problems with some settlement, causing some delays. Multiple contractors, 6 contractors all working on one project. If you'd left it to the contractors, you'd end up with 6 different instrumentation, 6 different systems, nothing talking to anything else, and the interfaces alone would have been quite complicated. So as a late initiative, what they did was they did something that they could implement quickly, and that is they implemented a process of sharing. Now, I've put this quote in here because this is exactly, I recall, this is exactly what the project director said in the meeting. Just because I'm a project director doesn't mean I'm not an engineer. I want to be able to see for myself. So this is the thing. So the senior people said, actually, I don't want to wait to receive that. I want to be able to see it for myself. So what we came up with was this concept of information partnering. And information partnering meant creating a charter how information was going to be managed on the job. Clear objectives at executive level. All 7 parties share the cost of a system, and the delivery consultant will manage that system delivery, and it needed strong leadership to change the behavior. If it's not in the system, it doesn't exist. Michael Chin said that at many, many meetings. Okay, don't bring the extra stuff, it's got to be in the system. And after a while, everything was in the system, and all meetings were run with that system up and on display. And after a while, it became very, very efficient. A number of people, I think Banjo is slightly involved in that project as well. So very, very useful, very, very quick. And in fact, it was so successful that our original 72-month contract only happened for 55 months because the job went so quickly. So we kind of shot ourselves in the foot there, but you know, it was just a very, very good job. Went very, very well. And one of the things that it did was the things that McKinsey have identified now in their talk about digital control towers. It created granular data available for engineers, simple to see, simple to visualize, give them access to it so they can really prove how good they can be as engineers. And you know, it's presented in digital twins, so you can see exactly what's going on. Even the engineers in the audience now can see what's going on this job. You can see the drawdown here, you can see the diaphragm walls and the shafts, you can see the movements, etc. And just by having that, we can identify easily potential problems. Here we can see that there is a silty sand layer at the top of the Booker T granite, which actually has a tendency to flow under hydraulic gradients. The diaphragm wall here was too short. So they recognized this early, actually managed to do some grouting down here at the bottom of this D wall before the excavation got at that level, and stopped having a major sand flow event at this point. So really good to be able to have this all data together so you can see the relationships. And again, here's live dashboards. This is going in and out of the rock in Singapore, and here's the guidelines for the face pressure, the interventions, and this is the slurry machine. So this is the actual rock excavation volume stamp here. You can see the level of control that we have. It's all open, willingly given by the people for the betterness of the project. So 2020 to present, collaborations and teamwork. Now you've already heard about the DTSS2 project from Banjo, another very, very successful project where a single system is provided by the client for the benefit of almost 30 contractors on the project. And on this project, actually, it was the engineers from the contractors on the SPPA job who then joined DTSS2 and were very keen to promote the same system on the job. Now, I don't know whether Banjo mentioned, but this happened to occur right in the middle of COVID, and for maybe a year or two, nobody could go to the office. So this system became everybody's virtual office for the project. They could see everything about the project and run all those everyday things they needed to do. So very, very successful. And it was then taken on Changi. So Changi Airport, the tunneling across the airport there was done very successfully using the same system. Great level of transparency. So just to say a sort of a status in terms of where the systems are at the moment, I put a little dot in here in terms of separate systems, not integrated. Currently, I think in Thailand, I think we're still having separate instrumentation systems and a separate TBM system, and they're not really put together yet. Same in the Philippines, same in India, our experience. The IDMS plus TBM data is happening now in Hanoi, in KBMRT, obviously down here. And then in some places, you can see that the owners are moving towards creating an owner system and putting that in place for the benefit of everybody on the project. And globally, we see, just in looking at the red here, you can see that more and more people are recognizing that the owner can implement the system. Now, it used to be that the owner didn't want to implement the system because of the risk of implementing a system. You don't want to have a problematic IT job as well as a problematic construction project. But now these are mature; they're off the shelf, so there is zero implementation risk of putting these things in place now. And this is sort of a change we're seeing in a number of places. In fact, the latest version of the Joint Code of Practice talks about the benefits of having just such project systems in place. So a last word about managing uncertainty. Okay. So having stuff in one place, is that ready? Okay. So one thing about having all this in one place is you can actually see the relationships between different sets of data. So I'm just showing you how this is a demonstration platform, but real data, how we can create a digital twin in real time with the latest information from the project, and it will put everything together into one model. Now, as part of that model, we can create ground models and bring in, which actually give a statistical assessment for what's like to come ahead. Now, this is from Kuala Lumpur. This is an example of a trial section of the VSM machine. You can see that we've got a wall cut through a volumetric model showing the R2D, and also because this is limestone, we can look at the probability there being voids. So this is a statistical calculation that says what's the probability there being voids, and you can see that actually there is a high probability there being voids along this tunnel alignment. And if we then link this to the TBM data, so I click on here and I can actually bring up the TBM parameters. And I can choose the face pressure. What we can do is say, well, okay, what happens to the face pressure? So you can see here that the face pressure was starting off in the green, and it's about 3 kPa. Then it drops off suddenly. So actually, that drop off coincides very well with the predicted location of this karstic ground. Now I can also look at the slurry density in here. So if I look at the density of the excavating chamber, we can see that whilst it was hit there, the high density slurry was gone on there. So it takes a while for them to do it. So this is just the trial section, but in a properly or a later section of tunnel, you would want to really to have that proactive view to the ground, to be able to see what's coming. And so often on tunnels I'm on, we don't have that. We don't have underground a view into the ground to see what's coming, not just in terms of the ground, but also in terms of any obstructions or if there's a utility coming up, where it is relative to the tunnel. But so this type of thing gives people the opportunity to see what's out there. And I liken it to driving a car with at night with the headlights off. You've got your dials, that's fine, but you can't see what's coming. And also, you don't have the navigation computer telling you where the next petrol station is. So this is a real sort of paradigm shift, really, in terms of how people can use data on tunnel projects. Now, that was going to be my last. Conclusion slide. One thing I wanted to show you, because it came up in one of the previous talks, is one thing that's often missing is the prediction. So I'm showing you here how within the mission platform, we can actually load here, we can load the prediction from Plaxis. This is actually your design software, loading data into the system, just as if it was an instrument. And what we can do then is we can then combine that data as a prediction at each stage for the actual observations. And the reason this is good, because it actually is showing you the design shape of the curve. Normally, it's just a single vertical line. Now, if you have a single vertical line for an alarm line, it means the toe could kick out by 50 times and you wouldn't have an alarm. So this is actually showing you this is what we expect the actual profile to be. And the same is true for settlement. This is the settlement above a tunnel, and we're looking at, this is distance from the tunnel face. So we're behind the tunnel here, and there we go. The tunnel comes to the face here, and then it goes after. So this is settlement over the top of the tunnel. And what we can do is we can create models in here that calculate that longitudinal Gaussian based on some parameters, the tunnel diameter and depth, but also a trough width parameter K here. So if I go into this model here, okay, and I'll just go and show you. Okay, so if I go into this proximity graph here, show you this one here, I can actually add a prediction. So if I go into a proximity settlement here, I can create a prediction. And what we do is mapping a predicted value to the observation using a trough width parameter. So let's just make this trough width parameter 0.4. Let's say that was the design prediction. So what I get there is I get a prediction. This is what I'm expecting to happen as the tunnel goes past, and this is what actually happened. And this gives us an opportunity to have alarms much more advanced than it would normally happen. Okay, we can see it's deviated from our prediction early. So I'm just by the face here. If it's deviating, we can put increased pressure on. If we go past the face, I've still got time to be able to put on increased tail grout pressure. Now, this opens up the opportunity for machine learning because based on this behavior, we can get the system to learn that that's not the right parameter. 0.8 is in these ground conditions. How do we do that? So by having design, prediction, by having observation, by having the ground all in one platform, it opens the opportunity to do a lot more machine learning, a lot more active feedback systems in the platform. So, in conclusion, passing all the risk to the contractors doesn't necessarily mean you're passing the risk, but it does mean you're passing a lot of control. And partly then controls the way the data is done sets the tone for a project. So we recommend setting up transparent, integrated quality data systems for the project, driven by owners. On the basis of that, trust but verify, and standardizes across projects, so that you can combine projects together and use that data to set benchmarks for other projects. Having data in lots and lots and lots of different systems makes it very difficult to use that for the future. Investing in systems is not a risk. This is now, as I say here, zero implementation risk. It's been done many, many times now. So controlling the way data is managed opens up opportunities really to streamline the project, accelerate completion. And ultimately, greater transparency reduces the risk every single time. We see this on every project we've done. Projects accelerate because the perceived risk is lower, both from the point of view of the owner, the contractor, but also from anybody who is a stakeholder surrounding the project can see that it's being managed well. And we keep being told, oh, but this is expensive. It's not. The cost of one single system versus the cost of many, many systems and the time taken for people to try and have to get this data and put it all together for their daily meetings, etc. It pays for itself. It is cheaper. It is a cheaper solution to have integrated platforms than it is to have things highly separated. Okay, so that was a sort of a quick journey through the last 30 years from our point of view as creators of these systems. As I say, my background was I was the person on a project experiencing the pain of not being able to get my hands on the data I needed. So that's why I created this company. That's why I created this system. So it is an engineering platform, and I think that's something that engineers really need. The ability to say, as McKinsey said, a digital control tower to enable them to get their hands on the data they need to do their job. So thank you very much for your time, and willing to take any questions. Again, apologies for not being able to be in Bangkok today. Thank you.
Thank you very much. And I really have to apologize to be the one who permanently asks questions. So,
no worries.
But let me reflect. My professional career started at the time when the hydropower projects along the river Danube from the German border to the Hungarian border all was done by construction companies, and these construction companies, they had their own design offices, they had their very special technology, and they have done it very successfully. And later I have been involved in the discussion in International Tunneling Association with regard to the risk management. And I have attended meetings at the British Tunneling Society in London, where we have decided on the risk management. It makes a lot of sense to have risk management, which was at that time at the brink of the insurance companies to stop every insurance for construction companies because they had to pay much more for damages which happened in the construction. than their income was. And it was logic that they have been thinking to stop insuring construction companies. Now, what you are telling me here today and what Dr. Richard has been also explaining before was management of data, and as much data are available and predictions also. It also makes a lot of sense that this is going to happen. And my question at the end of what I just said is, what is the benefit? Who is getting the benefit from that improvement of data management? Is it the insurance company or is it the construction company? I'm not sure if it is possible to completely eliminate uncertainty. I don't think, as long as we dig in ground and in rocks, there will always be a remaining uncertainty. And okay, I agree with you that this uncertainty can be limited if we feed our projects and from the design to the final completion and commissioning with data makes a lot of sense. But who is suffering? Who is having the benefit and who is having the disadvantage? Is it to the quality of the project finally, or is it to the schedule? So where are the benefits? If you can just explain a little bit more on that subject.
Certainly. I mean, the simple answer is everybody benefits. I'll give you an example. So after the joint code of practice came into place, on every tunneling project, you have to have an early morning meeting. And that meeting is called various things. In the UK now it's called SRG, Shift Review Group. Every excavation job on the project has to have a meeting. I was on Airport Link and they called it the Permit to Tunnel, PTT. I had to get up at 5 a.m. to spend 2 hours every day when I was down there helping out for a while, just to try and find the data to do my meeting. It meant chasing down surveyors and whatever, and that was painful to have to do that. And then half the time you got the data, it wasn't in a format that you needed it, etc., etc. You had to spend time processing it, whatever. So really, really hugely inefficient. So one thing that this has done, having these systems, is that has been completely taken away. So now the data is already available for you in a report, on the way on the bus to work. Then you can just review it and have your meeting. Now the meetings are done within the system using the blogging, and it's just totally streamlined. So people are enjoying that, and just that alone has saved a lot of time for people, a lot of pain, and also it's de-risked the job immensely. Because now they've got exactly the data they need when they need it, and it's quality and it's delivered quickly. So that's one area. Now, in terms of across the board, what we see all the time on these jobs where there is this transparency, where people get used to sort of sharing data and working together with data, is that confidence always increases. Okay, so confidence is good because you need everybody to be confident that things are being shared, that all the data they need to have, they have. It may not be everything, but at least they have it. And also, coming back to your thing about uncertainty, the question that the insurers really want people to recognise is, can we at least quantify the uncertainty? Okay, if we don't know something, let's be honest and say we don't know it. Let's not have a cross-section on a site office wall that is coloured in deep blue that everybody says, yeah, that's all limestone, when it's not. And in fact, some areas, they have a very low confidence about what it is. So we shouldn't have this sort of false sense of security. We should be honest about what it is. Now, we did this on a project in the UK where what they did was, instead of having that cross-section with a deep blue saying it's limestone, they actually had the shade of colour would sort of get fade out as the confidence in the interpretation was, decreased. And actually the contractors found that really, really helpful to know, okay, I need to go a little bit slower here, I need a little caution, maybe I should do probing, those sorts of things. So actually having that honesty in the data as well really helped everybody. So that confidence increased meant that they went quicker. It means there were less breaks on the project. It means people got into a good cycle, cyclic process, and it meant shorter meetings. It meant things just accelerated, and we see that time and time again. And then again, when it comes to commercials on projects, agreeing the data at the time was of great value to everybody, because it meant that when it came to settling claims, they just had to argue the process, not the data. So much time on previous projects was spent arguing the actual data, the actual facts, and that's a waste of time for everybody, including lawyers, to be honest with you. So there's just a few benefits. And another brilliant one was, going right back to that job we did in the 1990s. Had we not kept that data in such good form for phase one, they would not have had that data to predict phase two. And we're talking about predicting water inflow, predicting how many drill holes to drill, how much grout to pump, etc. That's not something you can get easily from boreholes, every 200 meters. So having that database of information was really good at coming up with empirical relationships to be able to predict things for future projects. So there's a few examples, and that's good for everybody. I mean, if that data is made available, as it was, it's good for contractors who are trying to tender a job and quantitatively estimate their risk as well in the project. I hope that answered your question.
Thank you very much. It was very comprehensive answer. Thank you.
Thank you.
Okay, thank you, Venkas. Actually, we prepare a token of appreciation for you, but since you cannot fly to Asia, so let Rich or Banjo keep it until you can fly to Asia or to Thailand.
I will be there. I'm hoping to be there in June. I'll be landing in Bangkok in June, hopefully. Fingers crossed.
Okay, yeah. Okay, thank you very much, Venkas.
Thank you.
So next, I would like to invite Kunarong to give closing remarks.
Thank you for everyone who joined this seminar. I think that I myself, I feel that this seminar is very interesting. So we have some speaking in Thai like me, and mostly we are presenting in English. I think this is the first time for the Council of Engineering who set up this kind of seminar for both languages. And I feel very happy to see all of the old friends and the young engineer. Some of them is age, like my son, but they will grow up the country in the future. We are slowing down, so I just try to transfer what is the knowledge that we are collected to my colleague engineering council. ขอบคุณทุกคนนะครับยังไงก็มาช่วยกันกับสภาวิศวกรหรือวทท.พวกท่านก็เป็นคนรุ่นกลางรุ่นใหม่พวกผมก็เป็นคนที่มีประสบการณ์ทำงานมาหลายสิบปีแต่มันก็จะต้องผ่านไปตอนนี้ผมก็มีแนวความคิดว่าถ้าเราทำงานมาหลายสิบปีเนี่ยไอ้ทฤษฎีเนี่ยมันก็คงจะเอาจากมหาวิทยาลัยหรือเอาจากนักวิชาการใหญ่ๆแต่บางทีเราก็พยายามที่จะมาส่งผ่านในเรื่องของประสบการณ์ซึ่งของพวกนี้แต่ละคนมันหาประสบการณ์ได้ไม่เหมือนกันนะครับคนที่มาทำงานทางด้านโดยเฉพาะอย่างยิ่งเนี่ยเรามาทำงานใต้ดินเนี่ยคนที่ไปทำเท่านั้นเองแล้วก็เจอปัญหาเนี่ยมันก็จะรู้แต่บางท่านที่ไม่ได้ทำท่านจบ Civil Engineer มาก็ทำจากข้างบนก็มองด้วยตาเห็นแต่นี้ไอ้พวกงาน Geotech พวกนี้มันก็ทำใต้ดินหลายๆเรื่องเลยเราทำโดยตามองไม่เห็นเราก็ทำงานสำเร็จจาก Feeling บางครั้งเนี่ยเราทำด้วย Feeling แล้วก็มันดีเหมือนเราคิดมันก็ดีแต่บางครั้ง Feeling ว่ามันจะดีแล้วมันออกมาไม่ดีผมก็เคยเจอแต่เพียงแต่ผมไม่คิดมากเราไปเจออะไรไม่ดีเราก็ต้องมาค้นหาว่าทำไมเรามี Feeling ว่ามันจะดีแล้วผลลัพธ์มันออกมาไม่ดีผมก็พยายามหาความรู้จากคนนู้นคนนี้อ่านหนังสือบ้างอะไรบ้าง สิ่งที่เป็นประโยชน์ที่สุดสำหรับผมเนี่ยนะคือบริษัทผมเนี่ยจะมีพวกมหาวิทยาลัยเขาส่งเด็กมาฝึกงานหรือบางคนเขาส่งมาทำเทสิสสมัยก่อนที่เป็นเสาเข็มหรือไดแฟมวอลรุ่นแรกๆมาทำเทสิสกับผมแม้แต่ดร.โอมอะไรพวกนี้ก็มาทำเทสิสเขาก็ได้ปริญญาไปไอ้ผมก็ได้ความรู้ที่เขาทำเทสิสนะควบคู่กันไปเราก็ผสมผสานกันก็เป็นอย่างนี้มาตลอดนะครับก็ผมคิดว่าถ้าบางท่านที่มีบริษัทแล้วก็จะยอมเสียสละเอาเด็กมาฝึกงานให้ทุนเขาบ้างผมจริงๆผมให้ทุนนักเรียนเนี่ยไปเรียน AT ปริญญาโทหลายคนนะฮะก็จบปริญญาเอกผมก็ให้ทุนไปหลายคนถึงแม้เราจ่ายสตางค์ไปแล้วเราเห็นว่าผลงานกลับมาถึงเขาจะไม่ทำกับผมหลายคนแต่เราเห็นความก้าวหน้าเขามันเป็นความภาคภูมิใจเพราะว่าความก้าวหน้าหรือความสำเร็จเนี่ยสุดท้ายมันก็เป็นของประเทศเราเท่านั้นนะครับก็ขอบคุณทุกท่านที่ท่านมาแล้วก็ผมกำลังคิดว่าผมจะให้เจ้าหน้าที่ผมเนี่ยเขาทำจดหมายไปให้ติ๊กมาสักนิดนึงว่ามาอยากจะเพราะปีหน้าผมก็จะทำอีกว่าเราทำอย่างนี้อยากให้เราทำไหมหรืออยากจะให้ทำแบบไหนคือบริษัทผมเนี่ยผมทำได้เพราะว่าจริงๆอ่ะมัน52 ปีเนี่ยมันก็มีกำไรสะสมมาพอสมควรที่เราจะดิสทริบิวให้กับสังคมของเราได้เพราะฉะนั้นเราก็จะทำแบบนี้ทุกปีแล้วโดยเฉพาะอย่างยิ่งผมก็เป็นอดีตกรรมการสภามาอยู่แล้วก็ช่วยเหลือสภาวิศวกรมาตลอดครับก็ขอบคุณทุกท่านนะครับวันนี้ก็คงจะเป็นเวลาที่เราจะต้องปิดการสัมมนา Now I think it's the time to closing this seminar Thank you very much my friend ขอบคุณนะครับ